So today we're going to talk about processor pipelining. We're going to start out talking about processor speed, and we're going to start out by reviewing the single cycle data path we had in the previous lecture, and then we're going to talk about how we can solve some of the problems from that with a multi-cycle data path, and then introduce pipelining. From there we're going to go on and we're going to talk about pipelining, and we're going to talk about what it is, and give some examples of how pipelining is used, and then we're going to motivate why we want to use pipelining. And that's of course going to be to get better performance. Finally, we're going to talk about how you build the processor pipeline. So we're going to look at the single cycle processor and how we cut it up to pipeline it. We're going to walk through some MIPS instructions in a MIPS pipeline processor. We're going to talk about the control logic, and finally we'll give some examples from the real world of pipelines. So there's some material that's not in this lecture. So from the book reading, there's nothing about the detailed control logic, designing instruction sets, and introduction to hazards. All of that stuff you should be reading in the book. So let's go ahead and get started talking about processor speed, or what it is that limits our clock. So here's the single cycle data path that we saw in previous lectures. And we talked about how for a single cycle data path, the speed is limited by the slowest path. So we gave an example of what might be the slowest path, and that was this one here. It's from loading the instruction through the sign extension, through the ALU, to the memory, and then back to writing. So this is a load instruction, and we said, well, if this is the slowest path, then what this is going to do is it's going to force all instructions to go this slowly. So for the single cycle data path, it doesn't matter if most instructions don't use the path, this is going to limit the clock speed. So here's a question. If accessing the data memory takes twice as long as any other instruction, and 30% of the program's instructions are loads or stores, how much of the time is the processor not busy? Well, the answer here is 35% of the time. So 70% of the instructions are not loads and stores, so they only need half the time to finish. So that means that half of that 70% is wasted, or 35% of the processor's time is wasted. So you can see that a single cycle data path can be very inefficient. So let's take a look at what happens with single cycle execution. So here we have three different types of instructions that take different amounts of time. And as we said, the clock cycle is dictated by the longest instruction time. So here type 2 instructions take the longest, which means we're going to have a clock cycle that's set to match type 2 instructions for all of our instructions. And as we saw in the previous slide, this is caused by different critical paths for different instructions. So let's take a look at the effect this has on a program. We've got a bunch of clocks here, and we'll shrink things down so it fits on the screen. And we'll put in some instructions. Instruction 1, 3, 3, 2, 1, and 1. And what you see from this here is the shaded area is all wasted time. This time is time the instructions don't need. So the one instruction here at the end doesn't need all of this time, but the clock has to be that slow because type 2 instructions do need it. So for single cycle execution, the slowest instruction determines the cycle time, and much of the time is wasted. So one solution to this is multi-cycle processors. Here the idea is that instead of having instructions take one cycle, we'll have instructions take multiple cycles. So this lets us have the fastest instruction determine the clock cycle, and slower instructions will just take more clock cycles. So let's take a look at an example from what we had before. Here are three different instruction types, and what we're going to do is we're going to have the fastest one take one cycle, and then we're going to use that cycle time to divide up the other instructions and have them take multiple cycles, hence the name multi-cycle processor. If we look at how this works out, we can see that the one instruction takes only one cycle, but now if we have a type 3 instruction, it's going to take 2 cycles. Similarly, a type 2 instruction is take 4 cycles. And if we now look at how much time is wasted here, we see it's much less. So a multi-cycle processor wastes much less time because you only waste sort of the leftover part from however many cycles you needed. The problem with multi-cycle processors is it's very complicated to keep track of all of this. So for each instruction, you need to know how many cycles it takes and what it's doing in each cycle, and each instruction is different. So having all these different instruction types take different number of cycles is very complicated to take care of. So, can we do better than this? And of course the answer is yes, and let's take a look. So what we're going to do is we're going to break up the instructions, as we did in the multi-cycle case, but we're going to break them up into the same set of phases. So each instruction is going to do the same sort of thing in each cycle, and each instruction will have the same number of cycles. So now the longest of these phases is going to determine the cycle time. So let's take a look at it. Here are some of our MIPS instruction types, and we're going to divide them all up into 5 cycles. So the longest phase now determines the cycle time, but we have more cycles per instruction. So we haven't come out ahead here. We've divided instructions into 5 parts, so we can run a clock that's 5 times faster, but we have 5 times more cycles per instruction. So we're not winning. What's going on here? So let's take a look at how this comes together in the MIPS pipeline. So here are instructions, and we're going to see how this maps to the actual processor. So the first part of the pipeline is going to be instruction fetch. So all instructions are going to do instruction fetch in their first cycle. That's where they load the instruction. Then in their second cycle, all instructions are going to decode what their instruction is and read the register file. In the third cycle, all instructions are going to execute using the ALU. In the fourth cycle, all instructions are going to read the memory. And in the fifth cycle, all instructions are going to write back to the register file. Now you'll note here that not all instructions do things in all pipeline stages. R instructions and branch instructions don't use memory. Similarly, branch and store instructions don't write results back to the register file. But they're still going to have a cycle for this so that all instructions have the same number of cycles and do the same things in each cycle. So, is this better? Well, this is what we've got. We've got our load and store instructions, and let's take a look at the resources we have. So in the first cycle, load is going to access the instruction memory. In the second cycle, load is going to read from the register file. In the third cycle, the load is going to use the ALU to calculate the address. In the fourth cycle, the load is going to access the memory. And in the fifth cycle, the load is going to write to the register file. And this is going to be the same for the R instructions and store instructions. Of course, R instructions don't actually do anything for the memory stage, and store instructions don't do anything for the register file write stage. Now let's take a look at we have this in our pipeline. So we're going to instruction fetch, instruction decode, execute, memory, and write back, and the same thing for the other instructions. And here's the cycle counts. So in order to figure out what's going on here and how we can take advantage of that, here's a question to look at. What is the ALU doing here in cycle 12? Well, it's not doing anything. In cycle 12, the store instruction is only reading from the register file. Nothing is using the ALU in this cycle. How can we take advantage of the fact the ALU is free here to be more effective in using our processor? So that's what we want to do with pipelining. We want to take the fact that the ALU is not being used in cycle 12 because our store instruction is just reading the register file to do useful work. In fact, if we look at this, these are all the cycles where the ALU isn't doing anything. The ALU is only being used in 3 of our 15 cycles. Can we find useful work for the ALU to do in those other cycles? If we can, we're going to get better performance. So this is what pipelining is. Pipelining is doing work in parallel. And what we want from pipelining is to use all parts of the processor for different instructions at the same time. So let's take a look at how we're going to do that. So here are the instructions we're not using the ALU. We want to find work where we can use the ALU at those times. Here's our load instruction, exactly the same as we had it before with our 5 pipeline stages. Now we're going to run our R instruction. But instead of having this start after the load instruction is done, we're going to have it run at the same time. So while the load instruction is doing instruction decode, the R instruction is going to start its instruction fetch. Similarly, while the load instruction is doing the execution, that is using the ALU, the R instruction is going to do instruction decode. And we're going to continue this way. So we've now overlapped the instructions, so we're doing 2 things at the same time in the processor. When it comes time to do the store instruction, we'll just continue this. So now we're doing the instruction fetch. And if you look what's happening here, we now have 3 different things happening in the processor at the same time with 3 different instructions. So the load instruction is using the ALU to do its execution. The R instruction is using the register file to read the registers, and the store instruction is using the program memory to read its instruction. We can continue this, and what you see is that we're using a lot more of the processor. We're doing multiple things at the same time, and this is why dividing up the instructions was helpful. So we divided up all instructions into 5 cycles, and they do the same sorts of things in each cycle, so now we can overlap them without it being too complicated. So here's a question. What is the ALU doing when the load is accessing the memory? Well, it's processing the R instruction's ALU operation. So in cycle 4, we have the load instruction accessing the memory, the R instruction using the ALU, and the store instruction doing instruction decode or accessing the register file. So 3 instructions doing 3 different things at the same time.